Hello Year 12 Extension 1, welcome to your HSC year, and while we've officially started Year 12, in Maths we have a couple of units to finish from the preliminary course. So we're going back to the chapter that we were working on before the exams, and we'll continue on with integration. Now, you'll hear me talk a lot about this, and I guess it's a problem-solving technique, or it's a way to approach every question in any topic, and it's with this see, think, wonder idea. So I'm going to encourage you to register what you can see in a question. Now, as you've heard me say previously, sometimes what you see is all you have. There are no words that you can give additional meaning to the question. It's just a diagram, and you have to pick out the main points of the diagram. Now, certainly that will be the case with a lot of questions involving integration, especially questions involving area. So you will, if you're given a diagram, I'm encouraging you to spend a lot of time looking at the diagram and identifying some key aspects of the diagram, which I will point out to you as we go through this exercise. Not only do you have to see and observe key features, I also then want you to do something with that. I want you to think. How will I use this information? What is the relevance of this? What is this telling me? Those sorts of things I want you to think about, and then wonder what sort of questions are they going to ask that is going to require me to use this information, or I wonder what other piece of information I need to bring to this question. What do I need to remember from previous topics, etc. Okay, so big emphasis on this see, think, wonder as a way of approaching any question. So exercise 11F is talking about the area of compound regions. Now, we have an example here of a compound region. In this diagram, this is what I would refer to, this grey shaded area, as a compound region. It exists under two different curves. So for some of the grey area, it's the area under the green curve, and for the remainder it's the area under the pink curve. Together, those two areas make what we call a compound area. This is just one type of compound area. It's not the only type, and throughout this exercise I will introduce you to the other types. Now, in this case, what do you see? Well, I hope I've pointed out you can see compound area, two different curves. We're finding the area under these curves and between the x-axis. Now, we know that's important because we saw previously that we could be finding areas between curves and the y-axis. So in this case, it's the area between the curve and the x-axis. What are we thinking about that? Well, I'm thinking, I wonder where one area finishes and the other one starts. I'm thinking that may require me to find a point of intersection because I want to identify x values. I'm wanting to add areas together here to get the total area of the composite region, etc. You may be seeing other points about the diagram, and by all means jot them down, ask me about whether they're relevant or not, and please pause the video at any time that you need to spend a little bit more time. Certainly if it's about what you can see in a question, or more probably commonly, if you want to think a bit more about a question, don't hesitate to pause the video. So we can see, hopefully, that we're going to need to identify the two integrals we need to add together. So let's set up our integrals for the area, and before we can actually set them up completely, we have to find this point of intersection. What is the x value where x squared is equal to x minus 2 all squared? Now, I'll just pause the video and do that little calculation. So you can see there that the point of intersection is 1. It looks like that on the graph, but we can't always take what's on the graph. We can't assume that a graph is drawn to scale, so we will do the algebra to confirm our point of intersection. So you can see that we want from 0 to 1 under the x squared curve with respect to the x-axis, and then we want from 1 to 2 under x minus 2 all squared with respect to the x-axis, so it's dx again. So there you can see that I've calculated the first integral, add 1, it's a nice straightforward integral. It's add 1 to the index, divide by the new index, sub in our values, and we get 1/3 units squared for that section. The second section is the integral from 1 to 2 of x minus 2 all squared. And again, it's a nice, easy, straightforward integration. Add 1 to the index, divide by the new index, and of course the coefficient of the x inside the bracket is a 1. And we want that from 1 to 2. Subbing in 2, we get a 0. Now be very careful. We're subtracting. Be very, very careful here. Can't emphasize that enough. Some of the most common mistakes that students make with integration is not their understanding of the process or their understanding of the diagram. It's just the arithmetic. Subtracting the next term. So 1 subtract 2 is a negative, and a negative 1 cubed is a negative, but we've got this subtraction of a negative, and subtraction of a negative is a positive. So we're having a third plus a third, which gives 2/3 units squared. How would we summarise that process? What you will need to do is to actually draw a sketch, unless obviously the sketches are given. Shade the region that it's referring to, find the point of intersection, and determine the individual integrals that are involved. I'm going to stop the video here and talk about some examples and subtracting areas in another video.